Like in the middle of the Oppenheimer-Snyder dust cloud, a point there where the density becomes infinite, and so the curvature of space-time becomes infinite.
What if everything we thought we knew about the universe was wrong? The James Webb Space Telescope has just spotted something so strange, it's forcing scientists to rethink how the universe even began.
James Webb begins a voyage back to the birth of the universe.
Some would say, let's invent a telescope that can see back to the Big Bang.
This distant galaxy doesn't fit the story we've all heard about the Big Bang. It's pointing to something far more mysterious. One of the boldest ideas comes from Nobel Prize-winning physicist Sir Roger Penrose. He believes the universe isn't a one-time event, but part of an endless cycle of death and rebirth.
The singularity remains constant.
It remains in there. You might say the size has gone to zero,
right,
but it could be quite complicated and irregular.
But even more shocking is his claim that there might be leftover clues from a previous universe still floating in our skies today. In this video, we're diving deep into what Webb has discovered and how it could change everything we know about space, time, and our place in it. Cosmic rule breakers. When the James Webb Space Telescope trained its astonishingly sharp gaze toward the familiar stars of the Big Dipper, it stumbled upon something both dazzling and puzzling. Those 7 bright stars forming a celestial ladle, or dipping spoon in the northern sky, seemed to host more than just nearby light. Hidden in their vicinity were faint glimmers from objects so distant that their light has journeyed across space for more than 13 billion years. These ancient beacons date back to when the universe was barely 500 million years old. Yet already they appear to have grown into giants nearly as massive as the Milky Way itself. Such rapid growth, according to conventional wisdom, simply shouldn't have been possible. Astronomers have affectionately dubbed these cosmic oddities universe breakers. The nickname hints at the way they challenge long-held models of how matter clumped together after the Big Bang. In a study published in Nature, an international team revealed how Webb's instruments picked up the faint glow from these far-off galaxies, then used that light to piece together a story of astonishing acceleration. By measuring how much the light's wavelength stretched, a phenomenon known as redshift, researchers could calculate how long it had taken the photons to reach Webb. That in turn told them the galaxy's ages, between 500 and 700 million years after the universe began. But age was only part of the mystery. By splitting the light into its component colors and gauging its intensity, the team estimated each galaxy's mass. What they found contradicted nearly every prediction of modern cosmology. These nascent islands of stars were already on par with the Milky Way. Current theories suggest that in the universe's first few 100 million years, there simply wasn't enough ordinary matter, nor enough time, to build such titanic structures. Yet here they are, luminous giants shining from the edge of time. "It's bananas," declared Erica Nelson, assistant professor of astrophysics at CU Boulder and one of the study's authors, during a press briefing. "You just don't expect the early universe to be able to organize itself that quickly. These galaxies should not have had time to form." The word bananas feels light, but it conveys the genuine astonishment rippling through the astronomy community. To reconcile these findings with existing models, astronomers must consider that star formation rates in those early galaxies were off the charts. By way of comparison, the Milky Way spins out about 1 or 2 new stars each year. According to Nelson, some of these ancient giants must have been cranking out hundreds of suns annually to reach their observed sizes in such a short cosmic span. That level of frenetic creation implies either an unexpected abundance of raw material, cold gas clouds ready to collapse into stars, or a dramatic rethinking of how quickly gravity can corral matter on large scales. This discovery raises questions that reach to the core of cosmic origins. Did the early universe hide shortcuts in the galaxy-building process? Might dark matter, the invisible scaffolding believed to shepherd ordinary matter, behave differently under extreme conditions? Or could there be yet undiscovered physics driving star birth at a pace far exceeding current expectations? Each possibility carries profound implications, not just for understanding galaxy formation, but for the very narrative of how the universe transitioned from a hot, homogeneous fog to the richly structured tapestry we see today. Webb's findings underscore the power of observing the universe in infrared light. Much of the early cosmos is veiled by clouds of hydrogen and dust, but infrared wavelengths slip through these barriers, revealing objects that optical telescopes simply cannot see. Equipped with instruments of unparalleled sensitivity, Webb has already rewritten chapters of cosmic history, from peering inside planet-forming disks to spotting ice clouds on distant exoplanets. With the Big Dipper pointing the way to more cosmic surprises, astronomers are eager to probe even deeper. Cracks in the cosmic code. Not long after the universe breakers stole the spotlight, Webb's gaze widened to reveal yet more surprises. Scattered across the young cosmos were galaxies so packed with stars that they seemed impossible for their age, just a few 100 million years after the Big Bang. But Webb didn't stop there. It delivered a second, even more startling challenge, a fresh blow to the long-trusted Hubble constant, which describes how fast the universe stretches. On paper, theory predicts a peaceful expansion rate of 67 kilometers per second for every million parsecs of distance. In practice, when astronomers measure supernovae, red giant stars, gravitational lenses, or pulsating stars, the number stubbornly climbs to about 73. That gap has puzzled scientists for years, but Webb's latest data didn't shrink it, it widened it. The mismatch grew more glaring, begging an even bigger question. Why doesn't elegant theory match gritty reality? Some researchers are now daring to dream up ideas that once sounded like science fiction. Picture our universe not as a lone island, but as one bubble among countless others, all bumping and merging in a vast multiverse. What if the universe's earliest growth spurt, known as inflation, wasn't just a random outburst, but the moment our baby universe slipped into a much larger parent cosmos? Armed with fresh math models, scientists simulated what happens when two universes collide and fuse. The results were astonishing. Under this scenario, the predicted expansion rate lined up far closer with what Webb actually saw. Suddenly, the wildest ideas in theoretical physics weren't mere thought experiments. They began to look like real pieces of the cosmic puzzle. The whole foundation of cosmology felt shaky. If the universe truly hangs on interactions with other universes, then every assumption about its growth, its shape, and even its fate might need rewriting. And a growing number of experts now admit that what felt like unshakable truth was actually just the best guess until nature revealed otherwise. The implications reach even deeper when the story shifts back to the darkness before dawn, the so-called cosmic dark age. This was a time when the universe lay shrouded in thick clouds of neutral hydrogen gas. Like a dense morning fog, the hydrogen absorbed and scattered ultraviolet light, preventing any glow from escaping. Nothing could shine through, and the cosmos remained hidden in a dim haze. Then came the first stars, igniting in pockets where gravity had squeezed hydrogen gas into hot, bright furnaces. Those newborn stars hurled out torrents of ultraviolet light, ripping electrons away from hydrogen atoms in a process called ionization. Tiny bubbles of clear, glowing gas began to form, each a beacon of light in the dark sea. Over time, these bubbles grew and merged until the fog dissolved, and the universe lit up in what scientists call the reionization era. Traditional models place the start of reionization around 300 million years after the Big Bang, with the process stretching over hundreds of millions more years. Early galaxies were thought to carve out only small bubbles at first, just a few million light-years across. Beyond those pockets, darkness held sway. Gradually, more stars and galaxies contributed their share of ionizing light, allowing the bubbles to swell and finally overlap, ushering in a fully transparent universe. Webb's observations, however, hint that this clearing happened much faster and more dramatically than expected. By peering into the infrared, Webb can detect the faint signatures of ionized gas and measure the sizes of those primordial bubbles. In several fields, the telescope found bubbles already tens of millions of light-years wide in a universe barely 500 million years old. That suggests galaxies were firing out ionizing photons at a pace far higher than models predicted. and that massive clustered star formation may have lit up the cosmos in a cosmic blink. Beyond the Big Bang. Instead of seeing the Big Bang as the ultimate starting line, a new line of thinking invites a wilder picture, one in which the universe we know is just one chapter in a never-ending story. Rather than a single explosive birth, our cosmos may have evolved through infinite cycles of contraction and rebirth. Each bang could mark not the beginning of everything, but a fresh chapter following the distant future of a previous universe. At the forefront of this bold vision stands Sir Roger Penrose, the 2020 Nobel Prize winner in physics. Penrose's idea, known as conformal cyclic cosmology, asserts that the universe passes through endless rounds of death and renewal. According to his view, the moment labeled as the Big Bang was really a transition point, where one universe's remote, stretched-out future folded into the fiery start of the next. Though Penrose first floated this scheme back in the early 2000s, it remains on the fringes of mainstream thought, partly because it asks people to rethink what beginning really means. One of the most challenging twists in this scenario is the fate of cosmic inflation. In the standard picture, inflation describes a blistering growth spurt in the first split second after the Big Bang, rapidly ballooning space by an immense factor. Penrose argues that this familiar tale is misleading. Rather than an inflationary burst immediately after the bang, the universe we see inflating now, the same self-similar, exponential expansion driven by a mysterious cosmological constant, simply continues unchanged across the transition. In effect, what looks like inflation at the universe's birth is actually a peak beyond the bang, into the dying echoes of a prior eon. That cosmological constant has its own curious backstory. Albert Einstein first introduced it to hold the universe in place, then famously dismissed it as his greatest blunder when observations showed the cosmos was expanding. Decades later, the term resurfaced under the name dark energy, a label that misleads, since it isn't truly dark or ordinary energy. In Penrose's scheme, this constant underpins both the late-time acceleration of our current universe and the mirror image inflationary expansion of the previous one. Because the cosmological constant drives a smooth, self-similar stretch of space, there's no need for a separate inflationary mechanism lodged at the Big Bang. In fact, adding a distinct inflation phase actually breaks the neat cyclic picture. Instead, Penrose shows that the same exponential stretch, seen today in supernova surveys and galaxy cluster mapping, would have governed the final moments of the prior universe, shaping the seeds that later bloom into stars and galaxies once the new cycle begins. This elegant recycling fits existing observations without tacking on extra assumptions. By peeling away the traditional inflation curtain, Penrose's theory links the slow drift of dark energy to the fiery dawn of each new cosmos. What emerges is a universe without a true beginning or end, an endless ebb and flow of structure fading away, then reawakening in fresh form. In each cycle, matter and radiation dilute until particles lose their mass's meaning, leaving only geometry behind. That geometry, shaped by the cosmological constant, transforms seamlessly into the hot, dense conditions interpreted as a Big Bang. Peering through this lens, familiar ideas fall away. The question, what happened before the Big Bang, becomes meaningful rather than forbidden. Instead of a singular birth event, there is a smooth bridge from one eon to the next, built on the same laws of physics that govern stars, black holes, and the cosmic web. Even the stubborn mismatch between theory and observation, whether in galaxy growth rates or expansion speed, might find fresh explanations once the universe's life cycle is seen as part of a greater, unending sequence. Whether Penrose's vision will stand the test of new data remains to be seen. Yet as Webb and other observatories keep probing deeper, each revelation about early stars, cosmic fog clearing, or the universe's expansion adds a new piece to the puzzle. If the universe truly dances to the beat of infinite cycles, then every discovery is not just a glimpse of our own chapter, but a clue to countless others. The cosmos, it appears, may be far stranger and far more poetic than any single story can contain. When galaxies dance, Rather than a lone cosmic drama, Penrose's vision paints the universe as a grand, never-ending saga, with chapters unfolding across epochs and eons. Even the collision course with the neighboring Andromeda galaxy fits neatly into this tale of cycles and rebirth. In a few billion years, the Milky Way and Andromeda will drift together under gravity's pull. Though it sounds dramatic, the galaxies won't crash like cars in a pileup. Instead, they'll pass through one another, stars weaving in and out like dancers in a slow, intricate ballet. Most stars, including the Sun, will sail by without a close encounter. But at the heart of each galaxy lies a monster, a supermassive black hole. Andromeda's beast is a heavyweight champion, far larger than the Milky Way's more modest black hole. When the two galaxies begin their merger, their central black holes will sense one another across the vast void. Over countless millions of years, they'll spiral inward, drawing ever closer like partners in a cosmic waltz. Eventually, the smaller black hole will be swallowed by the larger, its mass folded into the greater whole. That dramatic meal marks the birth of an even more massive black hole at the center of the newly formed galaxy. Yet even this grand event is just one episode in a far larger story. Our local group contains a handful of galaxies bound by gravity, each destined to merge in turn. But in the wider universe, there are clusters packed with thousands or millions of galaxies. Over unimaginable spans of time, these clusters will funnel matter into their centers, creating gargantuan black holes that outshine whole galaxies. After the last dance of galaxies and the final swallow of stars, the universe will enter what Penrose calls the boring era. Only black holes will remain, drifting through an expanding, empty cosmos. For around 10 Google years, that is a 1 followed by 100 zeros, nothing much happens. Black holes slowly leak energy in the form of Hawking radiation, a process so gradual that each quantum of energy takes eons to escape. As these black holes evaporate, they release faint trickles of energy into space. In Penrose's cyclic picture, all that energy doesn't disappear into nothingness. Instead, it carries forward into the next eon, imprinting a tiny mark, a signal of what came before, on the newborn universe. Most of this radiation is smothered by the dense hot plasma that fills the infant cosmos. Only after the universe cools, at the so-called last scattering surface, can any of it shine through. That surface, occurring roughly 380,000 years after each Big Bang, marks the moment when atoms first formed and light finally broke free. It's the origin of the cosmic microwave background, CMB, the faint glow that bathes the sky today. In that ancient afterglow, Penrose and his team believed they saw something extraordinary. Circular patterns of slightly higher temperature, standing out against the smooth haze. Dubbed Hawking points, these hotspots appear as tiny, concentric rings that don't fit standard models of CMB fluctuations. Penrose argues that they are the long-lost fingerprints of evaporating black holes from the previous eon, signals that survived the fireball of the new Big Bang and later shone through when the universe became transparent. Data from both the Planck and WMAP satellites revealed these rings independently, lending weight to the claim. The spots are faint and subtle, but they show up consistently in the same regions of the sky. To Penrose, this is more than coincidence. It's a whisper from a universe that existed before our own. Skeptics point out that random fluctuations can mimic such patterns, and that the statistics of CMB data are notoriously tricky. Yet the search for these Hawking points has sparked lively debates, fresh analyses, and new methods of data mining. If confirmed, they would amount to the first direct evidence of a cosmos before the Big Bang. Penrose's conformal cyclic cosmology reframes beginning and end in a way that feels almost poetic. There's no creation ex nihilo, no point when everything sprang from pure nothingness. Instead, each universe matures, ages, and transforms, passing its legacy through to the next. The laws of physics, especially the role of the cosmological constant, provide the thread that ties these epochs together. What emerges is a picture both humbling and invigorating. Rather than cosmic bookends, the Big Bang and the distant future become linked pages in an endless manuscript. Galaxies form, collide, and fade away. Black holes govern the universe's twilight, and their final breaths light the spark for the next great cycle. Each transition preserves a memory of what came before, encoded in the geometry and energy of space itself. For science, this idea is exciting and daunting. Testing it demands ever more precise maps of the cosmic microwave background, sharper surveys of galaxy growth, and deeper probes into dark energy's nature. As observatories like Webb push the frontier of what can be seen, and as future missions refine our picture of the CMB, the coming years may show whether Penrose's bold vision holds true. Now it's time for today's subscriber pick. Imagine the universe's birth wasn't the beginning at all. Nobel laureate Roger Penrose suggests something existed before the Big Bang, a radical idea shaking the foundations of science since the 1840s. If he's right, our universe may be just one phase in a never-ending cycle, and everything we know about time, creation, and existence could change. The implications are massive, and the scientific world is buzzing. If the Big Bang wasn't the start, then what was? The galaxy that should not exist. Webb's jaw-dropping find, JADES GS-Z11, reads like science fiction. Here was a galaxy blazing away just 330 million years after the Big Bang, yet already flooding its neighborhood with intense ultraviolet light. Even more astonishing, its glow carried the unmistakable fingerprint of Lyman alpha radiation, a telltale sign of energized hydrogen atoms. According to every rule in the book, that light should have been trapped, scattered, or absorbed by the thick neutral hydrogen fog still blanketing the young universe. Yet somehow JADES GS-Z11 shone right through. That cosmic fog, the dense clouds of hydrogen gas, was expected to swallow up Lyman alpha photons until much later in cosmic history. Models have long held that ultraviolet light struggled to travel more than a few tens of thousands of light years before hitting a hydrogen wall. But JADES GS-Z11 carved out a bubble of ionized gas a staggering 650,000 light-years wide. Suddenly, the universe at 330 million years old felt almost transparent, far sooner and more spectacularly than anyone dared imagine. Lead researcher Joris Wittstock of the University of Cambridge captured the mood perfectly. This was completely unexpected. Co-author Kevin Heinzlein didn't hold back either. We shouldn't have found a galaxy like this at all. And yet there it is. And the data clearly show that its UV radiation traveled farther than we ever thought possible. Those words hint at a bigger truth. Either reionization kicked off earlier than models predicted, or it surged ahead at a breakneck pace, reshaping the young cosmos in a hurry. Reionization has always been a slow, patchy process in simulations. Tiny ionized bubbles formed around each galaxy, then gradually grew and merged. But JADES GS-Z11's massive bubbles suggest that some galaxies punched above their weight. Perhaps the ultra-bright stars within burned hotter or formed in denser clusters, unleashing torrents of high-energy photons. Or maybe active black holes at galactic centers blasted out radiation powerful enough to clear vast regions of gas. If smaller or less massive galaxies were also pumping out intense UV light, they could collectively have driven reionization far more efficiently than previously thought. The idea flips a core assumption, that only the biggest, rarest galaxies mattered early on. Instead, a whole population of spirited underdogs, compact, star-packed systems, might have lit up the universe, one Lyman alpha burst at a time. Yet for all the intrigue, the mystery of JADES GS-Z11's power source remains unsolved. Was it a frenzy of super-hot, massive stars, or a ravenous black hole gobbling up matter and spitting out energy? Future observations will hunt for telltale signs: X-ray emissions, spectral lines from heavy elements, or the telltale flicker of an accreting disk. Each clue will help reveal whether star factories or cosmic vacuum cleaners ruled the roost. Beyond the nuts and bolts of reionization, JADES GS-Z11 dovetails with an even wilder idea, that our universe might be part of a vast multiverse, its growth and behavior shaped by collisions and mergers with other universes. Imagine countless bubble universes drifting in an unseen expanse, occasionally bumping into one another. Those interactions could stretch and twist space, boosting expansion rates and creating anomalies in cosmic measurements. Mathematical models of merging universes are already turning heads. When researchers simulated the aftermath of two universes fusing, the predicted expansion speed matched observations better than the standard model, echoing the tension between theory and reality that Webb keeps revealing. If our universe truly dances with neighbors in a cosmic network, each collision could send ripples through space-time, lighting up galaxies or punching holes in hydrogen fog earlier than expected. This multiverse proposal isn't just wild speculation. It's gaining traction as more data pour in. Webb's deep field images, combined with precise measurements of how fast the universe stretches, suggest something beyond simple dark energy or inflation. If merging bubble universes play a role, they could explain why certain galaxies shine too brightly, why expansion rates wiggle above predictions, or why Lyman alpha light travels so far so soon. Whether Penrose's cycles of rebirth, Webb's early UV champions, or the multiverse's cosmic handshake hold the key, one thing is clear: the universe isn't following the script. Each new discovery peels back a layer of certainty, revealing deeper puzzles and richer possibilities. The beautiful chaos of creation. The idea of an eternal cosmos is both humbling and thrilling, suggesting that existence is far more resilient and dynamic than ever imagined. Webb's discoveries are bringing this vision to life, revealing that the universe holds countless clues about its past, and perhaps its future too. Yet these findings aren't only about grand cycles or cosmic rebirth. They're also rewriting the story of how galaxies formed and evolved. In classic models, galaxies started as small clumps of gas and dust, gently merging over billions of years to create majestic spirals like the Milky Way. But the universe breakers, those massive star-packed galaxies Webb spotted, tell a very different tale. Instead of a slow, orderly dance, the early universe may have been a chaotic storm, with structures assembling at astonishing speed. Some researchers now imagine the young cosmos as a hotbed of intense activity. Gigantic clouds of gas could have collapsed almost instantly under their own gravity, igniting bursts of star formation and spawning black holes in a cosmic blink. Others go even further, suggesting that exotic seeds, perhaps primordial black holes left over from the universe before last, served as gravitational anchors, pulling in gas and stars at breakneck pace. Whatever the true cause, it's clear that galaxy formation in those first few 100 million years was a far wilder ride than textbooks once described. Black holes themselves emerge as key players in this drama. Many of the universe breakers bear the hallmarks of supermassive black holes, monsters millions or even billions of times the mass of our sun. Normally, black holes grow slowly, feeding on surrounding gas over millions of years. Yet here they were, fully formed when the universe was barely out of diapers. One idea is that these black holes sprang directly from the collapse of enormous gas clouds, sidestepping the slow accretion phase entirely. Another tantalizing thought is that they're heirlooms from a previous universe, survivors that slipped through a cosmic bounce and seeded the next cycle. Webb's infrared vision is crucial for unraveling these mysteries. By detecting the heat signatures of dust, gas, and the glowing disks around black holes, the telescope lets astronomers peer into the hearts of early galaxies. Each spectrum and image brings fresh clues: the mass of a black hole, the rate of star birth, the chemistry of ancient gas. Though the puzzle isn't solved yet, the pieces are falling into place faster than ever before. All of this carries huge emotional weight. For centuries, humanity has looked to the stars for answers, seeking to understand origins and our place in the grand scheme. The Big Bang Theory once offered a clear starting point, a single cosmic event that gave rise to everything. That narrative felt comforting, a neat moment when time and space began and life followed. But Webb's discoveries reveal that the truth may be far more complex and far more beautiful. Instead of a neat origin story, the early universe emerges as a living, breathing place of wonder and surprise. Galaxies raced to grow, black holes blazed into existence, and hydrogen fog was torn away in mighty bursts of ultraviolet light. Each discovery challenges expectations, urging a rethink of assumptions. And through it all, a sense of awe remains constant. The universe, it seems, is far more inventive and far more mysterious than any single theory can capture.